Now, welcome to the lecture 17th of course Polymer Science and Technology. In the previous lecture, we have seen that the rate kinetic equation for the step polymerization reaction in case of self-catalyzed polymerization. Now, continuing to that part of polymerization reaction, self-catalyzed polymerization reaction, we will see the molecular weight control. So we know that the xn is the degree of polymerization and xn bar is the number average degree of polymerization. This we have already studied in unit 1. So xn bar can be defined as the concentration of the monomer initially taken divided by the concentration of the monomer at any time t, and we know that the concentration at any time t is equal to m naught 1 minus p. Here m naught will get cancelled out, and xn bar, number average degree of polymerization, is equal to 1 over 1 minus p. This is a very important relationship that relates with the conversion with the number average degree of polymerization, and xn bar is an indirect measure of the number average molecular weight also. Okay, so from equation 5, where is equation 5? This is by equation 5. This is equation for self-catalyzed polymerization reaction. So from equation 5, xn, here in equation 5 it was 1 over 1 minus p whole square. So this will become xn bar square will be equal to 2 kt m naught square plus 1. So this is the equation of self-catalyzed step polymerization reaction in terms of number average degree of polymerization, xn bar. Note that xn bar in this equation is directly proportional to initial concentration of monomer taken, m naught. Xn bar is directly proportional to m naught, and xn bar is also directly proportional to under root times t. So we can say the number average degree of polymerization depends upon the under root of time. This is known as square root dependency. And what is the practical meaning of this? That if we increase the polymerization reaction time by 2, if we increase the polymerization, or if we double the polymerization reaction time, that doesn't mean that the molecular weight of the polymer will also be doubled, because molecular weight or number average degree of polymerization depends on under root times t. Okay, so it will not be doubled, it will be under root time t. So how to relate this mn bar, xn bar with the mn bar? We have already discussed this, but let's see once more. The number average molecular weight mn bar is equal to number average degree of polymerization xn bar multiplied by the molecular weight of structural unit m naught. Since the molecular weight of structural unit or repeating unit is slightly different than the molecular weight at the end, because at the end structure is slightly different, one additional hydrogen atom is added or any other group is added, so there is slight, very slight, or you can say negligible difference between m naught and m end. So ideally m n bar is equal to xn bar m naught plus m end group, but this difference is so minute when we compare the molecular weight of the polymer, which is in the order of several 100,000, and this difference is of just few units of the molecular weight. So we can simply neglect M end group. So we can neglect this. So my final equation will be Mn bar is equal to Xn bar multiplied by M naught. Here M naught is different than concentration M naught. Here M naught means the mean molecular weight of two structural unit, whereas this M naught is the initial concentration of monomer taken. So you have to keep in mind that initial concentration of the monomer M naught and this M naught is different. Okay, and M end group is the molecular weight of end group attached to the end of the polymer chain. So if we know the equation in terms of Xn bar, we can simply convert in terms of Mn bar. Correct. Now let us see the case of externally added catalyst. When in the step polymerization, polycondensation for step polymerization reaction, when we are adding a externally added catalyst. To achieve high molecular weight polymer within reasonable time, external catalyst HA is added. Example, HA may be a strong acid like H2SO4 or some other acid. Basically, HA must be capable of donating one hydrogen atom when required. Since the concentration of HA remains unchanged throughout the reaction, therefore the equation 3 can be written as, I hope you all must be remembering the equation 3 in the previous lecture. So the rate of disappearance of the carboxylic group is equal to K, capital K, which is the equilibrium rate constant, and K3, which is the forward rate constant in the step 2, multiplied by the concentration of the carboxylic group, concentration of the hydroxyl group, and concentration of the externally added catalyst HA, which remains unchanged during the polymerization reaction, because this is the catalyst and it will ultimately not participate in the reaction. However, in the formation of intermediate, HA is very much involved, but the concentration will remain unchanged throughout the reaction. Okay. Therefore, we can say minus M, here M is being taken as the concentration of either carboxylic group or hydroxyl group. So, minus d by dt M, concentration M, is equal to K dash M square, where M square relates to the concentration of the carboxylic group and hydroxyl group, whereas K dash is equal, it includes K, capital K, equilibrium rate constant, K3, forward rate constant, as well as concentration of the externally added catalyst HA. So this is my equation, and I can integrate this equation with respect to time t, and this integration from initial concentration M naught to the final concentration M during the time span t is equal to 0 to final time t is equal to t. Now this will give me minus mod minus 1 over M with the limit M naught to M and K dash T. Okay, so this is 1 over 1 minus M minus 1 over 1 minus M naught is equal to K dash T. Here I can put m is equal to m naught 1 minus p, as we have seen in the last lecture. So my final equation will be 1 over 1 minus p is equal to k dash t m naught plus 1. And here we know that this 1 over 1 minus p is xn bar. So xn bar is equal to k dash t m naught plus 1. So in case of externally added catalyst, the molecular weight or the number average degree of polymerization xn bar is directly proportional to m naught initial concentration of monomer, as in previous case. In previous case, this was also directly proportional to m naught. But if you look at the time dependency of the molecular weight, in case of externally added catalyst, xn bar is directly proportional to time t, whereas if you just recollect, in case of self-catalyzed polymerization reaction, xn bar was proportional to under root times t. Now let us see this. Here, in case of self-catalyzed polymerization reaction, the molecular weight or xn bar was proportional to under root of t. But in case of externally added catalyst, xn bar is directly proportional to t. So this is the main difference between the self-catalyzed polymerization reaction and externally added polymerization reaction. An externally catalyzed reaction gives high molecular weight in reasonable time, because xn bar is proportional to t. Here also we can find non-linearity in the lower conversion region, in the initial region, due to higher polarity of the reactant, and this characteristic is the characteristic of esterification, not the polymerization reaction. So in case of any esterification reaction, you will observe that the experimental data is deviating the kinetic model. Okay, so this deviation is because of the higher polarity of the reactant in case of esterification reaction, whether this esterification reaction is polymerization reaction or some other kind of esterification reaction. Okay. So now let us compare the kinetics of self-catalyzed and externally catalyzed polymerization reaction. In case of self-catalyzed, my equation is xn bar square is equal to 2 times kt m naught square plus 1, whereas in case of catalyzed polymerization reaction, xn bar is equal to k dash t m naught plus m. So my self-catalyzed polymerization reaction, where xn bar is proportional to under root times of t, is slower in terms of rate of reaction or slower in terms of rise of the molecular weight, whereas externally catalyzed polymerization reactions are fast and molecular weight will rise much quicker as compared to self-catalyzed polymerization reaction. And here if we compare the rate constant capital K of self-catalyzed polymerization reaction with the K dash constant of externally added catalyst, so K dash is much larger than K, and usually it is as high as double of K. So the externally added polymerization reactions, they are much faster in terms of molecular weight buildup. Now let us look at the assumptions of step polymerization kinetics. And the assumption for step polymerization kinetics is known as concept of equal reactivity. This is very important thing. You have to keep it in mind. Okay, what is the assumption for step polymerization reaction? Without this assumption, kinetics for step polymerization reaction cannot be developed. So there are two parts of this concept. The first part says that the reactivity of all the functional groups are equal. That's mean the reactivity of hydroxyl group or reactivity of the carboxylic group or any other group, they are considered as equal in case of step polymerization kinetics. However, the actual reactivity of functional groups depends upon the type of functional group. Okay, and they may differ from each other, but for simplicity or for the derivation purpose, it has been considered that the reactivity of all the functional groups are same and equal. The second concept is that the reactivity of functional group is unaffected by the reaction of one of the group. That's mean in case of a diacid, if there are two carboxylic group and one of the carboxylic group reacts with hydroxyl group or externally added catalyst HA, then the effect of reaction of one group will not affect the reactivity of the second group. Again, however, this is also not 100% possible, because once the functional groups are attached to a bulkier polymer chain, definitely the mobility of the entire diacid molecule will be hindered and it will affect the reactivity of the second functional group. But in order to develop the reaction kinetic of a step polymerization reaction, these two assumption has to be made. Otherwise, we will not be able to develop a mathematical model for step polymerization reactions. So keep it in mind, whatever is assumed is not in actual, okay, but we have to assume it for the sake of development of a mathematical model. Okay, so these assumptions are if not 100% true, but they are true up to a reasonable limit. Okay, so that's why we can make this kind of assumptions, but practically these assumptions are not at all valid for multifunctional reactants, okay, like 2,4-toluene diisocyanate, okay, where the reactivity of this NCO group are different because because of their attachment at the different location, at the ortho and para location. Okay, similarly here the functionality of the hydroxyl group attached to the first, second and third carbons, they are not same. So some multifunctional reactants, they don't show same or near same functionality. The functionality of the functionals group differ quite a lot. So these assumptions or the rate kinetics is not valid for this kind of reactant. So this is the end of lecture 17. I hope you must have enjoyed, and thank you very much for your patient hearing.